Hello everyone, this is Dr. Yuzo, and today we're gonna start to learn Module 2, Ohm's Law, KCL KVL, Nodal and Mesh Analysis. And before anything else, I wanna first of all emphasize the importance of this module. The Module 2 is the most important module, or say topic, in this entire course. And I won't repeat this the most important term again for any other modules. In other words, if you want to really learn something out of this course, please be noticed that this is the module. Ohm's Law, KCL, KVL, Nodal, and Mesh Analysis. Okay. Alright, so this module will cover number 1, Ohm's Law, which already known well by everybody, followed by so-called Kirchhoff's laws, including the KCL and KVL. So from their abbreviations, you can guess KCL means the Kirchhoff current law, KVL voltage law. And then next, we will try to conduct nodal and mesh analysis by applying those KCL and KVL's equations. The last, we will have many examples to practice. Okay, let's get started. 1. Ohm's Law. This is the first thing in this module, and the Ohm's Law is nothing but a IV characteristic relationship between the voltage cross and the current through of a resistance. We know the resistance is represented by R with unit of ohm, and the current through it equals to the voltage divided by the resistance value. As simple as this. And of course, we can easily imagine the voltage across it, VR, is equals to the product between the current through and the resistance value, if you want. And to find the power of the resistance, and then the power is equals to the product between voltage cross and the current through, as we know. But be careful the passive sign convention. That is a very important concern. Okay? And we can also derive this equation to different forms in terms of a current or voltage. Current squared times resistance, or voltage cross square divided by resistance. There's another term, new one, we need to learn, called conductance, represented by letter G in unit of Siemens S. It is the reciprocal of the resistance value. So you can imagine the power of a resistance could be equals to the current square divided by conductance, or equal to the voltage cross square times the conductance. And to Ohm's law, the key knowledge you need to keep in mind is actually here. It's about the voltage polarity and the current direction, following the passive sign convention. Here are 2 examples to demonstrate what's going on. So first, given a resistor with resistance value of 5 ohm, if you apply a current through it with this particular direction, the introduced voltage cross 5 ohm must follow the passive sign convention with polarity like this. Positive is at the current entering node. Negative is at the current leaving node. Similarly, if we apply a voltage with this polarity on a given resistance 3 ohm, the introduced current also must follow the passive sign convention, which is like this. The direction is entering the positive polarity of the voltage, leaving the node with negative polarity of the voltage. As to the magnitude of 4 ampere is quite straightforward. So voltage 12 divided by resistance 3 ohms equals to 4 ampere. So once again, be careful the passive sign convention it must be applied. 2. Let's talk about the Kirchhoff's laws. The first law is the current law. We call it KCL. There are two alternative ways to describe this law. It is describing one of the basic behavior of the circuit in any circuit. First saying is the algebraic sum of the currents entering any node is 0. So here it is talking about to a node in the circuit, all of the currents entering it equals to 0. Be careful, the currents here including the sign, positive or negative. And the alternative way to describe the same equation is the sum of currents entering any node is equal to the sum of currents leaving it. Be careful, the currents here have no negative sign. All of them are positive. In other words, their signs have been taken care by identifying the entering or leaving, like this. So either way to understand the same equation. Let's take a look at an example below here to see what they're talking about. So from this given circuit here, if you recall the concept of nodes, we should be able to identify up to 5 nodes. 1, 2, 3, 4, 5. So to each one of them, we are able to come up with 1 KCL equations in terms of obviously current. So let's see to node 1, what can we do? Based on the first description here, the algebraic sum of currents entering any node is 0. So to node 1, let's see how many currents or say branches involved here. So obviously 1, 2, 3. 3 currents involved in this equation. And they are respectively I1, I2, and I3. And what we need to see is I1 is actually current source current is entering the node 1. I2, I3, these are 2 currents leaving it. So how to write this equation based on the first description here? I1 as it is entering node 1, positive I1. I2, I3, they are leaving the nodes rather than entering node 1. So what we can do is flip their directions and also give their values, I2 and I3, a negative sign. And this is what we learned from previous module. Therefore, the equation we want to write is I1 plus negative I2 plus negative I3 equals to 0. In other words, negative I2 and negative I3 are the currents entering node 1 as well, same as I1 itself. Based on the second description here, the sum of currents entering the node is equals to the sum of currents leaving it. So the current entering the node is I1 itself. Place it at one side of the equal. And then equal to the sum of the currents leaving it. I2 plus I3 without giving any negative sign. It's not a surprise that these two equations are exactly same equation if you move the terms around. And therefore, we know these two are alternative descriptions. Feel free to apply any comfortable way to understand this KCL and accordingly write the equation. We can take an example on node 2. Let's see what do we have here. To node 2, again, we can tell 3 currents involved. I1 here, I4 here, and I6 here. So I1 this time is leaving the node 2. I4 as labeled here is entering the node. I6 is a third current leaving the node as well. So how to write this? I4 as it is plus negative I1 plus negative I6. In other words, I4 is entering node 2. Negative I1 and negative I6 are currents entering the node 2 as well. So you sum them up together equals to 0. Based on the second description, I4 as entering the node equals to the total of current leaving it, which are I1 and I6. So separate the currents entering the node and leaving it on two sides of the equal. Again, same equation. So either way works fine. Then let's see node 3 here. So node 3 in the middle here. First, you need to identify how many currents involved in this KCL. So obviously 1, 2, 3, and 4. 4 currents. And when you write them, you should follow first the sum of currents entering node 3 is 0. So you can tell I2 is entering node 3, I5 is entering node 3, I4 and I7 are leaving it. So when you write, you obviously write I2 entering plus I5 entering plus negative I4 entering plus negative I7 entering. The sum of them equals to 0. Let's try the second way. So again, I2, I5 entering the node 3. So sum these two together equals to I4 plus I7 who are leaving the node. So none of them has a negative sign in front, but they're placed on two different sides of the equal. Again, same equation. So you are seeing two different ways to write the same equation, always. Of course, I can tell you that my personal preference is actually the second way. I'm feeling separating the entering current and leaving current as more comfortable way to understand the circuit, but it's fine. Anyways, it's the same equation, as you know. So here are the KCLs for node 4 and 5, following the same idea. Now you can justify them yourself. Try both ways. And one obvious question is that what if the given circuit doesn't have the labeled current and its direction? Well, the answer is that you have to assume them at the beginning yourself, arbitrarily. It doesn't matter what current direction you are assumed. What you need to do is just follow the assumed direction to write your equations. Is your assumed current direction right or wrong? It doesn't matter. Okay? If you assume a wrong current direction, the resulted current value gonna be negative. So again, it does not matter. Feel free to assume any current direction at the beginning. The key is just to write the KCL equations accordingly. Okay, this is very important. You're gonna have to do this yourself in the exam as well. Assume the current direction along each branch yourself and write equation accordingly. Okay. Actually, the labeled current direction here, I2, I3, I4, I5, they are not necessarily the true current directions either. However, it's just a matter of positive or negative current in the result. Okay? Keep this very important point in your mind. So now let's take a look at the second voltage law. We call it KVL. There are also two alternative ways to describe the same nature of one of the circuit behavior. The first statement is saying the algebraic sum of the voltages along any direction around any loop is 0. So here we are not talking about node, we are talking about loop. And inside of this loop, we obviously need to assume a direction to rotate or say to follow. It could be clockwise or counterclockwise since we are talking about loop, which is closed path. And it doesn't matter which way. An alternative way to describe pretty much the same equation is this. The sum of the voltage along one path in any loop is equals to the sum of the voltage along the parallel paths in the same loop. So we're talking about two passes in the same loop. They are parallel. It sounds a little bit tricky, but we will see what they're really talking about by one simple single loop circuit below here. So to write a KVL equation for this loop, we need to choose, first of all, rotation direction. This direction could be considered as a current direction you're assuming. So either clockwise or counterclockwise, it doesn't matter. So here, if we are assuming a clockwise direction, so we pretty much talking about a closed loop like this. And we need to assume a starting point and make sure eventually we're going to come back to the same point. So let's choose node A as the starting point, of course also the ending point, beginning with which we rotate clockwise direction. We first of all come across the VR1, and VR1 has positive polarity before the negative polarity in terms of this rotation direction. So we are giving VR1 a positive sign in front. And then keep going along this loop. We come across this 5 volts voltage source. The polarity of this 5 voltage source is negative goes first, followed by positive. Again, we are talking about the rotation direction, right? Following which we come across the negative polarity first, followed by positive polarity. Therefore, we flip this 5 volts voltage by giving a negative sign in front of it. Next voltage we come across is the voltage cross R2, and with this polarity we can tell we are coming across the positive polarity first, followed by negative, so it's a positive sign in front of V2. So we continue here. The next one we come across along this direction is 15 volts voltage source again. And we come across the negative first, followed by positive polarity. So we give a negative sign in front of it. Next is VR3. Obviously positive first, negative after, so positive VR3. The last one is the 30 volts voltage source. We come across a negative again, so it's negative 30. After this 30 volt voltage source, we coming back to the origin point A. So we are done with this loop. The sum of them, all of the voltage terms, equals to 0. This is following, again, the first statement. Let's try the second statement to achieve, not surprisingly, the same equation. So we are talking about paths in the same loop. So obviously we need to choose two parallel paths. It could be any paths. However, from here, let's choose just from A to D. A is here, D is here. So-called two parallel paths means obviously from A to D this way, or from A to D this way. Right? These two are parallel paths, and let's see how to write the equation. So for this path up here, we are coming across the positive, negative VR1, positive VR1, as well as 5 volts. Again, 5 volts we are coming across the negative first, followed by positive, so it's negative 5. The last one from A to D, this path is VR2. So we come across positive first, followed by negative, so positive VR2. So this is pretty much the total voltage along this particular path and this particular direction. Let's see the second parallel path, also from A to D. Along this direction, we are coming across positive, negative 30, so it's a positive 30. Of course, this is already on the other side of the equal. And the next we come across is negative, positive VR3, so it's a negative VR3. And last one is the positive, negative 15, so positive 15. So sum them together at the other end of the equal. These two are same, according to the second statement here. So you can easily tell these two equations are same equations. So either way, here my personal preference again is actually really depends. Okay? If the given circuit is in loops or meshes like this one, the first idea, or say the first statement, is a better choice. However, actually in industry circuit schematics, you will see a lot of so-called pass circuits in where you can't see a loop. So the second statement would be a better choice. With those being said, in this particular course, the first statement is a better choice since we are not seeing much pass circuit. However, in future, if you are going to take like electronic circuits 318, 358, you will see a lot of pass circuits. But here in this EC 235, always loops. So let's see another simple example. Obviously, you're seeing more than one mesh. You're seeing two meshes. So how many loops here? Actually, we have 3 loops. Let's see, the first loop, I call it ABD loop. And we again assume the clockwise rotation direction. ABD is this loop with this clockwise direction. Okay. Loop 2 here, I mean BCD loop following clockwise direction again. It means this loop with this direction. The third loop, ABCD loop, with same clockwise direction. I'm talking about the big loop here. So let's write these 3 loops KVLs respectively. For loop 1 inside here, if we beginning with node down here, then we are coming across the negative followed by positive polarity of Vs. So we are having a negative Vs here. Next voltage we come across is VR1, positive, negative, so it's positive VR1. The last one is VR2, the voltage cross R2. As labeled here, we are coming across positive first, followed by negative, I think. So it's positive VR2. Sum them together equals to 0. And let's see the loop 2 here. If we are beginning from node here to rotate, the first voltage term we come across is this so-called 20 VR1. You need to be very careful here. This is a dependent source. And according to the symbol here, we can tell this is a voltage dependent source. And the voltage value is depending on another voltage. Therefore, this is a voltage dependent voltage source. The voltage across it is equal to 20 times VR1. So according to the polarity, we are coming across positive first, followed by negative. So it is positive 20 VR1. Next, positive, and then negative VR3. So positive VR3. Last one is VR2. According to the label here, we are coming across negative polarity first, followed by positive. So it's negative VR2. Sum them all together equals to 0. Last loop 3, clockwise direction. So we are beginning from node A here. Rotate this way. The first one we come across is VR1, so positive, negative, so positive VR1. Next is positive, negative, 20 VR1, so positive VR1. Next is positive, and then negative VR3, so positive VR3. Last one we are coming across is negative polarity goes first, Vs, followed by positive polarity of it, so it's negative Vs. Sum them up, we end up with this equation. I also provide the second statement idea to verify the same equation, so feel free to try them out and then let me know if any questions. Similar to the KCL, we also have a issue like this. Okay. So obviously the KVLs are all based on the voltage polarities you need to have at the very beginning. However, the given circuit in future obviously does not involve that. So you have to, no matter what, assume the voltage polarity of each term at the beginning. Well, the voltage source's polarity is very easy to be assumed or say recognized. How about the voltage polarity of the resistors? To answer this question, actually we just want to follow the assumed rotation direction, which could be considered as the assumed current direction. For example, in loop 1, we have assumed rotation direction, or say current direction, in clockwise, and then the introduced voltage cross R1 is just like positive here, negative here. This is how we assume the voltage polarity cross R1. Again, current flows through R1 in this way, introduce a positive here and a negative here, following passive sign convention. And this is how we assume the voltage cross R1 at the beginning, according to which we are write our KVLs.